Hello everyone, welcome to this session on algorithmic problem solving. In this session, we would like to look at the problem of the maximum stock span. So given the value of a stock for a range of days, the span of a stock for a given day is the maximum number of days you go backwards where the value of the stock would be less than or equal to the value on the given day. So this is a span for a single day, but we would like to find the span for each of the days given in the range. So let's look at the problem and the solution.
Let us formally define the span. Given an array A, span S I of A, I is the maximum number of values A, J, starting at position I and immediately preceding it such that A, J, is less than or equal to A, I. Span of any element is at least 1. In the example shown here, we have a sequence 6, 5, 4, 3, 5, 7 stored in an array. We would like to find the span of each element in the array. For each of the first 4 elements, the immediately preceding value is higher, so we cannot go further backwards. So, the span is 1 for each of the first 4 elements. For the next element, A, 4 equals 5. Looking leftwards, we encounter the subsequents 5, 3, 4, 5 which are all less than or equal to 5. Hence the length of the span is 4. For the last element, A, I, equals 7. But all 6 elements are less than or equal to 7. So, the length of the span is 6. Here are some queries of interest. Given the opening price of a stock today, we may ask the following question. When was the last time the stock value was higher than its value today? For instance, we may claim today's value to be a 52-week high if the span is 52 weeks or more. Here is a simple brute for approach. The span of an element is the maximum number of consecutive elements inclusive of the current element, and ones before it that are less than or equal to the current element. The algorithm efficiently computes the span for each element in a single pass through the input list. This makes use of the fact that it only needs to look back to find consecutive elements that are less than or equal to the current element. The Python code snippet here defines a function called span1 that takes a list, as input and calculates the span of each element in the list. The results are stored in a new list called slist, which is then printed. The time complexity of the algorithm is order n squared, where n is the length of the input list. Here is an improved algorithm using a stack. Iterate through each index in the input list. While the stack is not empty and the current element is greater than or equal to the element given by the index at the top of the stack, pop elements from the stack. If the stack becomes empty during this process, set the span for the current element to the current index plus 1. If the stack is not empty, set the span for the current element to the difference between the current index and the index at the top of the stack. We then push the current index onto the stack. The Python code for the improved algorithm is shown here. This algorithm takes order n time. Consider the following example sequence: 6, 5, 4, 3, 5, 1, 2, 3, 6. We will apply the second algorithm to generate the span of each element. The number in position 0 is 6 and its span is 1 by definition, since there are no other numbers to its left. We push 0 onto the stack. The number in position 1 is 5. Its span is 1 since looking backwards there are no other elements smaller than 5 to its immediate left. We push 1 onto the stack. The number in position 2 is 4. Its span is 1 since looking backwards there are no other elements smaller than 4 to its immediate left. We push 2 onto the stack. The number in position 3 is 3. Its span is 1 since looking backwards there are no other elements smaller than 3 to its immediate left. We push 3 onto the stack. The number in position 4 is 5. Its span is 4 since looking backwards to its immediate left, there are 4 elements including itself which are less than or equal to 5. We pop 1, 2, 3 from the stack. We push 4 onto the stack. The number in position 5 is 1. Its span is 1 since looking backwards there are no other elements smaller than 1 to its immediate left. We push 5 onto the stack. The number in position 6 is 2. Its span is 2 since looking backwards to its immediate left, there are 2 elements including itself which are less than or equal to 2. We pop the index 5 from the stack. Then we push 6 onto the stack. The number in position 7 is 3. Its span is 3 since looking backwards to its immediate left, there are 3 elements including itself which are less than or equal to 3. We pop the index 6 from the stack. Then we push 7 onto the stack. The number in position 8 is 6. Its span is 9 since looking backwards to its immediate left, there are 9 elements including itself which are less than or equal to 6. We have now successfully computed the span values for all the elements in the input array. Thank you. This course is brought to you by Elahay Technologies.